Let's jump right into this explainer and really unpack the hidden mechanics, the sheer engineering logic that actually makes modern high-speed rail possible. I mean, if you've ever watched a bullet train just slice through a landscape, you know it's an absolute marvel. But here's the thing. The real genius isn't just the sleek train itself. It's the incredibly precise track infrastructure beneath it and the strict operating rules that hold the whole thing together.
So here's our roadmap for today. We'll start by defining what high speed actually means, look at the four main system types, tackle the big speed conflict, and finally wrap up with segregation and maximum capacity.
Okay, let's kick things off with Section 1, defining high speed according to the UIC standards. Right off the bat, the crucial thing to understand here is that high speed is not just a fast train. No, it's a completely harmonious ecosystem. You've got specialized tracks, advanced trains, and rigorous operating rules all working together. You literally can't just slap a jet engine on a standard railcar and call it a day, right? The International Union of Railways, the UIC, emphasizes that these three elements have to work in absolute unison to pull off safe, commercial, high-speed travel. Now, the UIC actually splits this definition into two main pillars. You've got entirely new infrastructure, and you've got upgraded classical lines. If you're building completely from scratch, well, your tracks need to be equipped for at least 250 kilometers per hour, which paves the way to eventually push past 300. But say you're navigating really tough topography or cutting through a dense city, in that case, you can simply upgrade existing lines to hit speeds around 200 kilometers per hour. And that brings us to a very important number, 250 kilometers per hour. That is the absolute minimum speed threshold you have to hit on a newly built line to officially join the high-speed club. It's basically the magic number. It dictates literally everything from your curve radii all the way down to your power supply. Of course, reaching those blistering velocities safely requires some truly state-of-the-art rolling stock that operates in total lockstep with the track geometry. I mean, think about it. At these speeds, you're trying to minimize aerodynamic drag, manage heavy axle loads, and maintain this perfectly precise fit between an angled steel wheel and a steel rail. Engineers call this balancing act equivalent conicity, and it is honestly a spectacular engineering ballet. Moving right along, let's hit Section 2, the four system types and track compatibility. So the ultimate operational destiny of any railway really comes down to how the traffic flows. Basically, high-speed trains can either stay entirely exclusive on their own isolated tracks, or they can heavily mix with your standard classical trains. And the choice an engineer makes right here, it fundamentally changes the capability of the entire network. Let's break these down a bit. Japan operates what we'd call the purest Type 1 exclusive system. It's a totally closed network just for bullet trains. Now, skipping past some of the hybrid models, we see a Type 3 system in Spain. There, high-speed lines are shared with gauge-changing conventional trains. And then finally, you have countries like Germany and Italy using a Type 4 system where high-speed and conventional trains just freely mix across the board. The specific decision a country makes between these four types dictates its track geometry, the maximum axle loads allowed, and ultimately its overall maintenance costs. Basically, the purer your system is, the easier it becomes to maintain those microscopic track tolerances. And that's absolutely crucial, because keeping heavy, unpredictable loads off those rails is exactly what guarantees you that incredibly smooth, glass-like ride when you're hurtling along at 300 kilometers per hour. Which brings us to a major headache for engineers. Section 3, the speed conflict between passenger and freight trains. Look, if you try to mix a 300 kilometer per hour bullet train with a heavy, lumbering freight train, you immediately trigger a cascading nightmare of delays, track damage, and safety hazards. First off, the fast trains completely eat up the operational paths of the slower ones. Second, those incredibly heavy freight axles practically destroy the delicate geometry of the track. And third, you create some severe aerodynamic dangers inside tunnels. Let's zoom in on that scheduling conflict first. Because a bullet train closes distances so incredibly fast, it needs a massive empty safety buffer ahead of it. To put that into perspective, because of this huge speed differential, just one single high-speed train will actually consume the operational path of 3 or more slow-moving goods trains on that exact same track. So by mixing speeds, you are literally deleting capacity and creating an enormous bottleneck.
On top of that, the sheer physics of those heavy freight axles grinding down on the rails makes it basically impossible to maintain the delicate track geometry you need for safe high-speed running. The studies are super clear on this. Heavy freight trains permanently warp the horizontal alignments and vertical curves, and those are the exact features a passenger train relies on to stay safely on the tracks at 250 kilometers per hour.
And it gets scarier in two-track tunnels, where mixed traffic creates terrifying aerodynamic pressures and severe safety risks. Imagine a high-speed train passing a slow freight train in an enclosed space. It acts like a giant piston, creating these incredibly dangerous pressure waves. To prevent a catastrophic accident, high-speed trains are often forced to heavily reduce their speed inside tunnels, which, let's be honest, kind of defeats the whole purpose of building a high-speed line in the first place, right?
So how do we fix this? That leads us to Section 4, segregation and maximum capacity.
The most effective answer, as study after study has proven, is total segregation. You simply have to pull the freight off the high-speed line to maximize both safety and capacity. I know it sounds incredibly simple, but isolating your high-speed passenger traffic from your heavy goods traffic is truly the golden key to unlocking the full potential of your railway network. For example, Indian Railways looked at this exact strategy for their future lines. Their solution: construct a brand new, exclusive high-speed corridor. Then, by shifting standard passenger trains onto that new corridor, they magically free up massive amounts of space on their old tracks for those lucrative freight trains. It's really a brilliant two-for-one solution. It drastically increases the overall network earnings while simultaneously modernizing passenger travel.
But okay, there is a catch here. You can't always fill bullet trains to the brim all day long from day one. So to avoid leaving a brand new expensive line underutilized, operators can intermix 350 km/h trains with conventional passenger trains. But critically, and this is key, those conventional trains must run at a minimum of 140 km/h. Doing this narrows the speed gap just enough to prevent those severe traffic bottlenecks we were talking about earlier.
So, to quickly summarize the taxonomy we've explored today, mixing passenger speeds is an acceptable compromise if you need to build early capacity. But mixing high-speed passenger trains with heavy freight, that's an engineering nightmare that destroys tracks and creates huge aerodynamic dangers. When it comes down to it, the exclusive high-speed corridor remains the absolute pinnacle of rail engineering.
Which leaves us with a really critical engineering question for the future of global travel. As our populations grow and our cities become more connected, what kind of system will your region choose to build? Will it rely on a compromised mixed railway, or will it push for a perfectly segregated high-speed ecosystem? Think about that next time you take a train. Thanks so much for joining me on this explainer, and keep looking closely at the incredible engineering operating quietly all around you.